Good afternoon. Like some of you, I'm part of a team that develops and runs a number of services in the cloud. And like many of you, I enjoy going to the movies on weekends. These two activities should be compatible, right? It was a weekend a couple of years ago. My friends and I were going to the cinema. We were all excited about watching the newest sequel or prequel or maybe a remake of a movie that we actually liked. Little did I know that that evening, instead of watching a comedy, I was going to become a character in my own disaster movie. Because when the movie was about to start, I had a bad feeling about that. And unfortunately, I was right. When I looked at my phone, I did not receive good news. I was being paged because an alert had gone off for one of the services owned by my team. For every incident in an Atlassian system, a Jira ticket and a HipChat room are created. I quickly joined the conversation using the HipChat mobile app. There, I met other responders who had also been paged and were already working on the problem. One of my teammates told me that the service dashboard was illuminating like a Christmas tree. We quickly realized it was not a false alarm. There was an outage, and customers could not access our services. At Atlassian, we take outages very seriously, because we know that you depend on our services to do your job. Following the protocol for situations like this, a war room was set up. This allows the team to focus on the problem and to communicate efficiently. We were struggling to understand the cause of the problem. Multiple and very different services were simultaneously failing. Although the operators were restarting those services, after a few seconds of hope, the problem was coming back. With every second of downtime, the pressure to restore the service was building up. Some of you may already have experience with situations like this. And you will agree with me that they are not pleasant. I would rather be at the cinema watching the movie than sitting in a war room. Eventually, we figured out what was happening. At the time of that incident 2 years ago, we had a reverse proxy in front of a number of different services, some of them with low availability. Normally, the web request will come to the reverse proxy and be routed to the appropriate backend. The reverse proxy was using a single thread pool to dispatch all those requests to the different backends. Normally, that wouldn't be a problem. But what happens when one of the backends is slow or completely unavailable? Because of the high traffic, soon all the threads in the reverse proxy will be waiting for responses from that failing backend, leaving no threads available to serve requests for the other backends. In this case, the reverse proxy was allowing one of its dependencies to monopolize its resources, dramatically decreasing the availability of the whole system. We realized that a fault in one of the components of the system was triggering a chain reaction that was causing the unavailability of the whole system. Other areas of engineering know this problem very well. They even have a name for it. They would say that our system was not fault-tolerant. Fault tolerance is a property of a system that enables it to continue to operate in the event of a fault in one of its components. The definition does not require that the system operates perfectly under every possible circumstance. For cloud services, some kind of graceful degradation is usually acceptable. So what is a fault? A fault is a deviation from the normal state. Faults can have many causes. Some of them have internal causes, like a software bug, and some of them have external causes, like a sudden increase in the traffic. In any case, a fault only affects the internal state of the system and is not observable from the outside. Only when the problem bubbles up to the surface, there is a failure. Two typical failure modes in cloud services are total or partial unavailability and degrade performance. In enterprise software, failures cause your business to lose money. They can also damage your reputation. For high-profile services, failures can become a trending topic. So we clearly want to avoid failures. How can we do it? Well, you could think that if failures are the external manifestation of faults, then we could prevent failures by eliminating all the faults. That seems to make sense. Unfortunately, that's not realistic. The truth is that technical and economical reasons make it impossible to prevent all failures. For example, we simply do not have the technology to deflect an asteroid that is falling towards a data center, no matter what you may have seen in the movies. Down to earth, we cannot build hard drives that last forever, or reliable networks that work all the time, or bug-free software. Therefore, we must approach this from a different angle. We must acknowledge that everything may fail and will fail. And we must focus not on preventing those failures, but on preventing them from escalating into a system-wide failure. That's easier said than done. Unfortunately, we cannot build availability into our systems because availability is a derived property and not one that we directly control. Fortunately, there are other properties which we can control with our decisions about how to design and implement a system. One of those properties is fault tolerance, and the key to obtain fault tolerance is through stability. Systems can be classified into stable and unstable. A stable system resists small deviations and tends to return to its initial state. On the other hand, an unstable system can be permanently pushed out of its nominal state even by a small deviation. In this talk, I'm going to introduce 5 techniques that you can apply as soon as you come back to your workplace. Using these techniques, if you work with cloud services, you can make them more fault-tolerant. I will also present 5 examples of how we at Atlassian have learned the importance of these techniques and how we apply them to our cloud services. The first and most basic of those techniques is to contain the fault. The idea is very simple. Set up physical and logical barriers to reduce the blast radius of a fault. If you look around you in real life, you will find examples of this everywhere. Buildings like this, for example, have fireproof doors, which prevent the fire from propagating from one room to the next. Or at least, they slow down the propagation, giving people more time to save their lives. Another example of physical containment are the bulkheads, which are the steel walls inside a ship that contain the ocean water into a small subsection of the boat in case of a breach in the hull. That metaphor of bulkheads is also being used in the world of cloud services. In computing, containment applies both to hardware and software. Data centers, for example, have multiple networks for different classes of traffic. There is a network for production traffic separate from a network for remote backups and another one for administrative functions. In that way, if one of the networks is congested, the other traffic is not affected. These days, any self-respecting cloud service runs in a cluster of multiple computing nodes. A load balancer sits in front of the cluster and distributes the traffic among the nodes. The load balancer can also monitor the health of the nodes, and it can restart or replace faulty nodes. Combined with the inexpensive availability of virtual servers and containers, there is no excuse not to run multiple copies of your service. In that way, if one of the servers melts down due to a fan stopping or any other hardware or software problem, only that server will be affected, but the service will continue serving traffic from the other nodes. Containment also applies to logical resources inside an application. For example, many applications use thread pools to manage concurrency. If your application has a single thread pool, if one part of the application becomes slower, threads will inevitably concentrate there. Instead, consider having multiple thread pools for different kinds of tasks, like accepting connections or running batch jobs. Another example are the connection pools, which applications use to talk to remote APIs or databases. Again, consider having a separate connection pool for each dependency. That reduces the efficiency of the service, but in exchange, it increases its robustness. The choice of communication mode also affects fault tolerance. By definition, synchronous point-to-point communication, like most of the REST APIs, require that both the sender and the receiver are available at the same time. If the receiver is not available, the message cannot be delivered, and that propagates the fault from the receiver to the sender. On the other hand, asynchronous communication decouples the availability of the sender and the receiver. In this case, if the receiver is not available, the message is just put in a queue, and the sender is not affected. Moreover, when the receiver recovers, it can catch up with the backlog of queued messages. When possible, prefer asynchronous communication using technologies like message queues, SQS, Kinesis, or Kafka. Let's see an example of containment. And in fact, I'm going to go back to the example at the beginning. That system based on a reverse proxy was not doing a very good job at containing failure, and that ruined my movie night. Due to some particular circumstances with that system, it was very difficult for us to improve that implementation. So instead, over time, we completely replaced that system with a better architected one. But the story does not end there. The team learned the lesson very well. And more recently, the same team was working on another critical system at Atlassian, one with multiple clients. Then a new client came. This new client was much larger than any of the previous ones. In fact, it will double the load on the system. Although the team performed load testing and was confident that the system could absorb the new load, a strategy was implemented to minimize the risk at launch. So instead of doubling the size of the existing cluster to cope with the extra load, the team deployed a new independent and parallel stack of the same service just for the new client. In that way, if there were any surprises, the problems would affect only the new client. So to summarize these first and most basic techniques, we must set up barriers to contain the scope of a failure. Look for those single points of failure that act like multipliers of the effects of a fault, and try to eliminate them. One simple way to do that is to invest in redundancy. The Space Shuttle used to fly with 5 redundant, very expensive computers. For a fraction of that cost, you can have multiple computing nodes behind a load balancer. That was the first technique. The second one is to fail fast. The fail fast principle says that a quick error is often preferable to a slow response. That may sound a bit counterintuitive. If some part of the application is being slow, wouldn't it be better to give it more time before giving up? Well, in practice, errors and slowness are correlated. If something is taking longer than usual, chances are that it may fail anyway, so waiting will be in vain. But more importantly, waiting is one of the worst things that we can do, because it reduces our options. Instead, when something fails fast, we have many options at our disposal, like aborting, or retrying, or activating an alternative path. Even when some component of the system is failing, the system as a whole may still be able to deliver value, but only if it reacts quickly. Failing fast also frees valuable resources like threads and connections for other parts of the system to use. There are multiple tactics that we can follow to fail fast. I will discuss 3 of them. The first one is early validation. It is pointless to start processing a transaction, acquire the necessary resources like a connection to the database, only to discover later that the transaction cannot be completed because, for example, it contains a syntax error. Do not leave validation to the database. Push it outwards to the API of your service. Look for opportunities to turn back requests without doing much work. If you're writing a REST server, your service should return a 400 bar request status code for invalid requests, instead of passing down the call to the persistence or business layer. Going one step further, we could think of rejecting not only invalid requests, but also perfectly valid requests when the system is under stress. Your service could detect this by measuring the length of its queues or the usage of its pools, and in that case, immediately reject additional traffic. When a REST service rejects requests due to overload, a 400 bad request is not the appropriate status code, because there is nothing wrong with the request. Instead, a 503 service unavailable is the polite way to tell REST clients to please come back later. In my experience, the lack of strict timeouts is the main contributor for cascading failures. The general rule is very simple. Any operation that is slow or blocking must have a timeout. The shorter, the better. Never, never, never wait indefinitely. For those of you who, like me, are software programmers, software engineers, setting timeouts is probably the simplest way we have to make our systems more fault-tolerant. While some of the other techniques that I discuss in this talk have more to do with the design of the overall system, timeouts are part of our daily job. Every line of code that we write, we should think whether it's a potentially slow operation and make sure we set up a timeout around that. Let me give you a few hints about where to look for slow operations. The first place is in process logs. These are often found around shared resources or critical sections. A very common scenario is checking out a resource from a connection pool. If the thread has not been able to acquire the resource after a short period of time, it should simply back off. Most applications also have some kind of database. Queries to the database can be slower than you think, or they may be trapped in a deadlock. If the result has not come back from the database quickly, it may be already obsolete, so there is no point in waiting for long. Networks are known to be unreliable. Even something as simple as a DNS query can be surprisingly slow. There are two main timeouts that we should always set when dealing with the network: the connection timeout and the read timeout. Beware of network libraries that hide or abstract these details out from you, because if you cannot set your own timeouts, you will be at the mercy of the library defaults or the operating system defaults, which in some cases are measured in minutes or have no timeout at all. And finally, calls to remote APIs, of course, must have a timeout. If you're writing your own REST client, make sure you correctly configure the timeouts in your HTTP client. Let's see an example of the importance of failing fast. For that, I will introduce another one of our services. We run 2 copies of this service in 2 different geographical regions, and we have configured database replication between the 2 geographies. We thought we had a great story about availability. The theory was that if we lose the database in one of the regions, we could fail over to the other region. One day, we decided to test that theory. We put one of the databases behind a firewall to interrupt all the network traffic. And then we triggered the database failover. Unfortunately, the service remained unavailable for much longer than we expected. The service was waiting for network responses from the database that would never come back because there was a firewall in between. We fixed that by changing the timeout of those connections to a much shorter timeout, allowing the service to quickly recycle its connections and effectively fail over to the other region. So, to summarize, a quick error is often preferable over a slow response. Look for opportunities to turn back requests before doing much work. Do not hesitate to refuse service when in trouble. The clients of your service would appreciate your honesty, and they will change their plans. And most importantly, remember to always set timeouts around anything that may take longer than an instant. That was the second technique. The third one is pure common sense. Just stay away from trouble. Think about the electric circuit breakers at your home. They have 2 positions, open and closed. Normally they are closed, which means that they connect the wiring of your home to the grid. However, when there is an overload, they automatically switch to the open position, and that physically splits the circuit in 2. The mission of a circuit breaker is to be the weakest link of the chain and to protect the rest of the components of the system from an overload. We can borrow that idea and use it also in our services, especially around integration points like REST APIs. Let's see how that works. Imagine that we have a client and a server, and that we install a circuit breaker between them. Normally, the circuit breaker will be in the closed position, and that will allow all the requests from the client to hit the server. The circuit breaker will just sit there monitoring the results of all those requests. However, if the server becomes unavailable or slow, those requests will start failing or timing out. The circuit breaker will detect that, and when the error ratio exceeds a configurable threshold, the circuit breaker will switch to the open position. When in the open position, the circuit breaker will immediately interrupt and fail all the attempts to make requests from the client to the server. That has benefits for both the client and the server. For the client, it will not waste resources making requests that have a high chance of failure. And for the server, which is having difficulties, incoming traffic will stop. If the problem was originally caused by an overload, that gives the server a chance to recover. Of course, the circuit breaker will not stay open forever. Instead, from time to time, it will allow a fraction of the traffic to pass through. When the server recovers, those exploratory requests will succeed. The circuit breaker will detect that and will switch back to the closed position, resuming normal traffic. Circuit breakers are a phenomenal defense against a cascading failure. However, they are very complicated to implement. My recommendation is that you use an open source library. The most popular one is Hixtrix by Netflix. Hixtrix is much more than just circuit breaking. It also provides a framework to set up timeouts around almost anything. You can configure the fallback behavior for your circuit breakers. So instead of just failing the request, you can return a default value or a cache value or activate an alternative path. Finally, another feature of Hixtrix is monitoring. Hixtrix comes with a web dashboard that displays the status of all the circuit breakers in your system, and that acts like a proxy for the status of all the dependencies in your system. Let's see an example of circuit breakers. For that, let me introduce another one of our services. This service started its life as a big single-tenanted service. That means that we used to run a copy of this service for every tenant. That was very inefficient, so we decided to implement its architecture. The first thing that we did was to split the service in two: a stateless front end containing the business logic, and a stateful backend dealing with the persistence of the tenant data. Then we replaced the front end with a multi-tenant service, but still talking to the tenanted backends. But wait a second, look at the picture. Haven't we seen this before? Yeah, it's the same picture that we saw before when talking about the reverse proxy. We realized that a failure in one of the tenanted backends could again compromise the whole system. Our response to that was to install circuit breakers between the front end and the backends. In that way, if one of the backends is in difficulties, the request for that tenant will of course fail, but the other tenants will not be affected. As one of the engineers on call for this service, I'm very glad that we installed those circuit breakers. We have seen them working many times. So to summarize, in order to escape from trouble, you first need the ability to detect trouble. You can do that by measuring some metrics like the error ratio and comparing them to thresholds. Once you confirm that there is a problem, you should not continue doing the same thing because it's not going to work. Instead, think about your options. You may be able to find and use an alternative path. The fourth technique is to adjust. Anywhere where an interaction takes place, the parties should communicate their expectations and they should keep each other updated about their status. A good example of that is the TCP protocol, which underpins the internet. As you may already know, when two internet hosts want to open a connection, they follow a three-way handshake protocol, which allows them to agree that they are ready to exchange information. And then, once the connection is open, the parties dynamically negotiate a TCP window, which is the number of packets that can be in flight at any given moment. If the receiver is congested, it will reduce the size of the TCP window. That will cause the sender to reduce the speed of the communication, and that will avoid saturation. We can apply those ideas not only to network protocols, but also in the application layer. For example, if query boundaries and pagination prevent surprises when querying a database. Without those limits, the application cannot anticipate the size of the result. If the result of a query is unexpectedly large, that may cause trouble to both the application and the database. Another powerful technique is to use streaming of those responses. Streaming can be used both with databases and also with REST APIs over HTTP, and that optimizes both the memory consumption and the latency. As our applications run, they tend to accumulate resources like disk space or memory. Sometimes this accumulation is part of their normal operation, like populating caches or keeping log files or an audit trail. In those cases, it is our responsibility to design mechanisms to keep the size of those things under control, for example, by evicting caches or rotating log files. In some other cases, however, the accumulation of resources is unintended. It is the result of a bug, like a memory leak in a hash map. Make sure you always set limits for any data structure that may grow. Flow control allows the parties to dynamically adjust the speed of the communication to their current needs. REST services, for example, can push back to their clients by using rate limiting or request throttling. If you have a producer and a consumer and they work at different speeds, you can smooth the difference by adding a buffer, but make sure that the buffer has a limited size. Finally, if you are running in the cloud, you can use auto-scaling to dynamically adjust and match the capacity of your consumers and your producers. And finally, retries. Again, the idea is very simple. Insist a few times before giving up. However, it is notoriously difficult to implement retries correctly. And unfortunately, a poor implementation of retries decreases stability instead of increasing it. Firstly, it is not okay to retry every possible error. There are transient and permanent errors. If you're working with REST APIs, those are roughly described by the 500 and 400 families of status codes. It is okay to retry after a transient error, but it is pointless to retry after a permanent error. Secondly, retrying an error immediately until the operation succeeds is a recipe for disaster. Instead, the caller should back off, which means that it should wait longer and longer periods of time between retries. And if, of course, it should have a timeout, the shorter the better. By backing off and timing out, the caller maximizes the chances of success, while at the same time, it gives the system a chance to recover. The example I have selected for this, it's a bit embarrassing. In this case, we had a front-end and a back-end service, each one deployed in its own cluster so we could scale them independently. One day, we observed something new. Every time that we added a new node to the front-end cluster, within seconds, one of the backends would die. What was happening? Well, it turns out that before joining their cluster, the new front-end nodes were running a deep health check. And as part of that deep health check, they were checking the connection to their backend. For that purpose, they were using an unbounded query. That went unnoticed for years. But one day, the backend had accumulated so much data in its database that the results of that unbounded query simply did not fit in memory. So ironically, a request from the front end to the backend to ask, "How are you doing?" was causing its death. We fixed that embarrassing oversight by changing that unbounded query to a bounded query with a fixed cost. So the summary for this technique is that components in the system should not only look after themselves, but also after the others. Avoid operations that have an unpredictable cost. Feel free to retry, but do it smartly to avoid making things worse. And try to design components that can adjust the speed of the communication to the current status of the system. And that brings us to the last of the 5 techniques. This one is about learning from experience. No matter how well designed your system is, the ultimate benchmark is how it behaves in production. Once you have deployed your service to production, you must collect metrics about its behavior to understand what it's doing. How many transactions is it processing? What is the 99th percentile of the response time? How many nodes in the cluster are healthy? Among the most important metrics, you must calculate the availability and reliability of the service. Display that information using dashboards, analyze trends, find anomalies, and set up alerts. By now, you may be already convinced of the need to make your service more fault-tolerant. But how do you test if your service is indeed fault-tolerant? Well, you could deploy to production and just wait for the next outage of your cloud provider to see and discover then if you have done your homework well or not. But a smarter way to test is to continuously introduce turbulence into your environments. This is known as chaos engineering. Two prominent tools in this area are the Chaos Monkey by Netflix, which randomly destroys computing nodes in your cluster, and Toxi, which is a proxy that poisons the network communications. At Atlassian, we enforce the testing with Chaos Monkey as part of the process that every new service must follow to graduate and be declared ready for production. In any case, despite our best efforts, things will always and inevitably fail in production. At Atlassian, we see each incident as an opportunity to learn and to make our services and our processes more robust. By routing, we analyze every incident to find the root cause. We capture our learnings in Confluence, and we raise follow-up actions as Jira tickets to ensure that those things get fixed. If you want to learn more about our incident investigation process, please check the Atlassian playbook in our website. In the previous examples, I have already discussed how teams and Atlassian learn from the experience and become better at building services. Now, let me tell you a story about testing. In this case, my team was working on an event sourcing system. The service here on the left was generating events and saving them as rows in a database, in our case, DynamoDB. A fundamental property of event sourcing is that the data store is append only. That means that once you have saved some information, you cannot modify it. We were having some throughput issues because, as you can see in the picture, we were saving each event as a separate request to the database, and that was very slow. Fortunately, DynamoDB has a bulk write operation, so we decided to make use of it to save multiple events with a single request. Once we implemented that, we obtained the performance boost that we were after. However, before we could deploy that to production, one of our Bamboo builds started failing. That Bamboo build was running a set of acceptance tests, and it was using Toxi, which is the proxy that introduces chaos in the network. In our case, we had configured Toxi to randomly drop 10% of the network packets. Normally, that wouldn't be a problem for our service, because if one of the events cannot be saved, the service would just retry and save it later. However, when that happened, there was a window between the first request and the retry in which another request could come and save a different event with the same identifier. There was a violation of that fundamental principle of event sourcing. Fortunately, we detected that before going to production, thanks to that build. And that saved us from an incident in production with potential data loss. That story illustrates that it pays off to test with random chaos to validate your assumptions about the behavior of the system in the presence of faults. Make sure you collect information about what your system is doing in production, and when incidents happen, learn as much as you can to become better at building services. And that was the fifth and last technique. To recap, in this talk, I have given you 5 techniques to make your systems more fault-tolerant. The first technique is to contain the failure, because a fire in a small storage room should not burn down the whole building. The second one is to fail fast, which lowers the cost of failure and releases resources that can be used elsewhere in the system. The third one is to escape. If you see a fire in front of you, just go in the opposite direction. The fourth one is to adjust the communication to avoid misunderstandings and overloads. And the fifth one is to learn from mistakes, because you should never suffer the same disaster twice. In conclusion, in order to ensure the survival of our services in production, we must adopt a new attitude. Life as a service is very complicated. Just imagine for a second that you are one of your services in production. Your dependencies are actually your enemies. The execution environment is hostile, and the users will do anything they can to hurt you. Trust any of them for a moment, and you will be dead. Instead, we must acknowledge that everything will fail, and we must engineer around those failures. Forget about pretending that you can prevent all the failures. Instead, focus on preventing those failures from escalating to a system-wide failure. And finally, it is tempting to assume that the life of a project concludes with the successful release of version 1.0. The reality for software is that most of its life happens after that initial release, so we must prepare and invest for the long term. The main takeaway from this talk is that we cannot prevent all failures. No matter how low the probability of an event is, if it is not zero, it will eventually happen. Instead, focus, as I said, on preventing those faults from escalating into a disaster. When you run systems in production, your quality of life after the release 1.0 directly depends on the robustness and stability of your system. Build those properties into your system, and you will be able to enjoy movie nights without interruptions. Not to mention that next time you will be the hero of the movie, because you will save your company from a costly and embarrassing incident. If you are interested and you want to learn more, I highly recommend these two books. And with that, thank you very much for your attention, and special thanks to my teammate Luis, who had the initial idea of presenting this talk. Thank you.